Okay. Sweet. So, thanks for listening to me. My name is Andrew Nordman, and you're stuck listening to me, and I'm going to attempt to convince you to stop making web applications and instead everybody build robots. That's my goal. As mentioned, I'm Andrew. You can find me on GitHub at Kidwallian. You can find me tweeting and retweeting silly things at Kidwallian. You can find me talking about beer on Homebrew Talk at Kidwallian. And if you want to find me on Google+, there's the number. People wonder why Google+ is a barren wasteland. As mentioned, I work at Articulate. We are an e-learning technology company. They focus more on creating software to help other people teach rather than trying to teach you things. I work there on their online presence, and we are hiring. So if you are one of those rare unicorns of Ruby developers that are unemployed by choice, or not by choice, feel free to find the Mohawk. I would like to talk to you. By night, I am the co-founder of Cadman Brewing Company. It's a very, very small brewery. You probably haven't heard of it. History lessons. We are based out of Sycamore, Illinois, which if you have heard of Sycamore, Illinois, then bravo. There's probably one other person as well. And we focus on a variety of different beer styles and trying to push the edge on the traditional stuff, which requires a lot more emphasis on process control, which is what got me into this mess in the first place. We're not hiring, we're not looking for taste testers, and we're not looking for free feedback. If you'd like to buy some beer, then you can talk to me, find the Red Mohawk. When I'm not doing one of those two jobs, I am a father of two. And I tried to get a nice picture of my family before leaving, and of course the 3.5-year-old said, no, I don't like pictures. So he's the one hiding back there. And as far as I'm concerned, the role of father is to figure out exactly how little sleep you actually need in order to function, decrease that by an hour. And I wish we were hired, but we're not. So I want to preface this talk with the fact that I love Ruby. I love Ruby. Ruby. Rails, let's just be friends. I like what Rails has done in order to promote Ruby, but the fact of the matter is, when you talk to the average person about Rails, they'll either have never, or Ruby, they'll have never heard of it or think that Rails and Ruby are the same thing. So I take the viewpoint that we need to look at Ruby as a perspective of what can we do besides Rails? What can we do besides web development? Find something else and push it there. And that's why I submit ridiculous talks like, hey, we're going to start making video games using Ruby, and then talk about them. And in this case, we're going to make robots, and I'm going to show you a robot. So first, let's talk about what is an embedded system. I alluded in my talk title that we're going to embed it into your daily life, and that was a pun. Apparently, at least one person didn't get that it was a pun. It's about, I'm going to use the definition that a computing component embedded within a larger electromechanical system or device is an embedded system. The logic board that focuses on the overall state machine that interfaces with another board, which then interfaces with a physical device, or a microcontroller that is handling the overall logic and interfacing with a physical device. The emphasis there is on the physical and also on the concept of single purpose. Your computer is not necessarily an embedded system because it's general purpose. It's meant for doing whatever. You're not running a single program that does everything. You're running a series of sub-processes on top of the operating system, which in and of itself is yet another series of sub-processes. And so I got into the world of embedded systems mainly through brewing and the idea of process control. And as I started looking into how embedded programming works and how embedded systems are structured, I started to realize that I was coming from the Ruby world, seeing a lot more of, and more importantly the web development world, is seeing a lot more parallels to service-oriented architecture presented into a physical medium. And so one of the other concepts that you have to shift out when you're looking at service-oriented architecture is also the concept of you're moving outside of the digital and into raw hardware voltage logic. So the concept of voltage logic is that you're not sending binary code across to translate what's going on or passing messages across. You're instead sending actual electrical signals, which the components have certain minimum threshold of power, in order to understand the high and low states, and that will in turn trigger physical changes and manipulating to however you're wanting. So in this instance, the CPU is setting 3.3 volts at 40 milliamps, and the component doesn't have any idea what that logic is, because the CPU is running on 3.3 volts and the component's running on 5 volts. And so now the CPU has to, in order for the component to understand what the idea of true and false is, or on and off, or high and low, the CPU needs to be sending the appropriate voltage across for the component to work. So now you've got the complication of not just debugging all of your code, but hey, I happen to be running a 3.3 volt CPU and all my components are 5 volt, now I get to work with new levels of problems. Because the one thing that a programmer really needs is another layer of places to debug. So as I mentioned, as you start to get into more complex embedded systems, you start to notice that everything kind of falls together under subsystems. And you have individual controllers that are handling subcomponents, which are handling the physical interfaces, and you start writing interfaces between those particular components. And you end up with these nice little gray boxes with red boxes and blue boxes and green boxes. And not just because I like those colors, but also to demonstrate the fact that you end up having a lot of state control over here. And everything is running in isolation until you need to bother the motor control system, for example. This is a terrible diagram of how you would handle a motor being controlled by remote. So I fire off a signal using my IR emitter. The IR sensor picks up something, interprets the sensor, sends it to the main control saying, hey, I just picked up a signal. Main control system says, really? All right, let's fire a motor, and it starts spinning some servo motors. But the main control doesn't handle that. The motor control system handles that. The motor control system then sends commands to the motors, the servo motors themselves, which are controlling something else, and we've got layers within layers. So I started looking at this and going, yeah, that looks an awful lot like web apps that I start writing, and now let's put Ruby in it. So can we apply software-oriented concepts of physical computing of isolation? And I say, yes, so let's do it. So how do we do that? The first thing that we need to do is find a way, a physical medium in which to interact with. And I brought several goodies today. The first ones that we're going to take a look at utilize what's called general purpose I/O. What they use is it's a series of expansion pins that allow you to tap into the operating system and the physical hardware to extend the capabilities of the particular board. So if you want to start tacking on LEDs and create awesome pyrotechnics off of them without explosions, or if you want to start making a robot, or things of that nature. The pins themselves don't have a particular purpose. Just like the concept of the voltage logic and it being on and off, you're not sending particular commands. It's up to you to figure out that layer. I can look right here, I don't have to curl my head. Let's look at the giant screen. So the biggest component that is useful for us is the fact that it's using Unix file handles in order to be able to write in the different states of these general purpose I/O. It doesn't have any preconceived notions. So down here you'll see an example. We are turning on pin 17. We are telling it that it's going to be an output pin on line 2, and we're going to set the value to high. And then the Unix system will be able to handle the GPIO module within the kernel will be able to handle the fact that it's going to turn that on. So we then physically connect to one of these fantastic little pins on here, and now we have power coming through it. Don't worry, it's not enough to kill you. That's one of my other projects. So you might be thinking, hey, I have heard of Arduino. That's something microcontroller-y. Can we just jam Ruby into an Arduino directly? And the answer is no, because it can't take much more of it, Captain. Instead, the Arduino runs off the Atmel Virtual Runtime, or the AVR. It's the single microcontroller that's on there, and it only has about 8 kilobytes of SRAM. That is not enough to run a Ruby virtual machine. So it makes it very sad. See, Ruby can't go in there. So what else can we do if we can't use Arduino? Well, first up is the Raspberry Pi. You may have heard of the Raspberry Pi. If you haven't, I'm very sorry, but now you're going to have to hear about Raspberry Pi, so I guess it's not a big deal. Raspberry Pi is a low-cost computer. It was originally designed, the first model was $25. The Model B is $35 and included an additional USB port as well as an Ethernet port on it, and also runs considerably more power. It has 26 available GPI pins and a variety of different communication protocols designed for you to focus on education and teaching people about electronics, as well as just having general access to computers as a whole. It runs a custom distro of Debian, but you can change that to whatever variety of Linux you really want if you feel hipster and feel that you need to run Arch Linux for whatever reason. It's very, very useful, and at the low cost, it's a great way for people to get into physical computing without having to spend a lot of money. They used to have a problem with supply. They have finally caught up on all the orders, so it shouldn't take you too long in order to acquire one. The other board that I've only recently started working with, but I've been incredibly impressed with, is the BeagleBone Black. This is slightly more expensive at $45, which, by the way, everything that I'm going to be showing today is $50 or less. And I'm not trying to sell you any of these things. I just like putting dollar numbers on here. It also runs a custom Linux distribution. It has 92 GPIO ports and is designed less on education and more on developers that are hacking things and want to make really complicated stuff. It's very pretty. It's all black. It's a brand new model. I'm going to rip it out of the floor. Ooh, look. One of the things that's most interesting for me about the BeagleBone Black is not the fact that it's got more ports or the fact that it has a faster processor. They're both technically, the Raspberry Pi and the BeagleBone Black are both running ARM processors. They're both running on 3.3 volt logic levels. It's that it actually has its own built-in version of Cloud9 IDE running on it, shipped straight with the Linux distribution. So what you can actually do is plug it into your main computer, fire up your browser, access that version of Cloud9 IDE, write the code, run the code through Cloud9 IDE, and watch your physical indications actually working on the board. So it's a whole lot less than having to either use SSH and manipulate that way or plug up an HDMI in order to use it. Very fun, very useful, and if you don't like JavaScript, then we'll ignore that part because the entire thing's running on Node.js. So how do we access it? We've got this physical board. Now we need the ability to actually utilize and manipulate this stuff. I kind of like manipulating stuff using just straight echo commands and catting out to things, but that's not Ruby, that's scripting. So someone developed the library called wiring pi in Python. Python's not Ruby, you're saying, but there's a Ruby port, and it works basically exactly the same, and it's made by the same people that made wiring pi. The concept is quite similar. If you've ever dealt with Arduino, they model it very similarly. You instantiate a new global of the wiring pi interface. You specify input and output modes on your particular pins, and then based on if you set it as an input mode or an output mode, you have reading or writing capabilities. Don't try and write to a read or read to a write. It'll go, what are you talking about? And most importantly, the most annoying part about this library, and I think I'm going to have to submit a pull request in writing these slides, is that they don't namespace the globals on input and output. Unacceptable. Everything else is namespaced except input and output. So don't get messed up by that. So now, we have a means. We have a board. What can we do with this? Well, for my purposes, beer plus Ruby equals Bruby. There's no equal sign there, I just implied it. So for me, brewery automation, with working in recipe design, there's a lot of emphasis on, as I mentioned, blocking out particular elements and ensuring that you can have stability from one batch to the next. If you go to a bar and you order a beer, you expect that the first time that you had a pint of that beer and the last time that you had that pint of beer before you die is exactly the same, with a little bit of leeway, which means that you need to control a lot of the elements. For people that are not familiar with homebrewing, just out of curiosity, how many people are homebrewers, have homebrewed, or know what homebrewing is? Sweet. I added that last one because I wanted to see more hands. Concept is pretty straightforward once you get into large-scale brewing. You take grain, you throw it in a large container, you heat up water to a specified temperature, you put the water in with the grain, you hold that temperature for a long duration, sugars get extracted out of the grains, you then boil it, add hops, throw some yeast in it, hope that you didn't screw anything up, and the yeast will do their job and make beer. Yeah! That's a lot of steps that can potentially go wrong. For example, that water needs to be at a specific temperature in order to cause a specific reaction. And it needs to be held for an extended period of time, which is variable depending upon the beer style. You need the boil to be at a certain rate, because it can't just be a boil, it has to be a rolling boil in order to be able to remove certain chemicals that are commodities. So there are a lot of different steps there. So what I needed to have was a means of removing the variable of boil control and temperature control. That meant that I also needed to be able to control heat using water heating elements, and I also needed to be able to control and regulate and monitor the temperatures of the beer even after all of the boiling is done and the yeast are doing their job. And I got things to do. I got 2 jobs and 2 children, and that's way more hours than apparently I'm allowed to have my prefrontal cortex focusing on. So what I did is I took temperature sensors, I took a Raspberry Pi, and bolted them on and had it constantly polling the temperature and sending it up to Ruby and saying, hey, it's this temperature. How about we run a PID algorithm in order to determine how much power we need to output in order to control the heat of the liquid in order to make the temperature that I want for that time frame. And that worked. Great. Now we need to move on to temperature control on the other side. Well, I need to use temperature sensors again. I need to run the code in order to monitor and then change cooling systems instead of heating systems on the fermentation side to drive down the temperature. So there's my particular use case. Beer, logs, all the things. I actually have it originally when I gave a portion of this talk on brewing beer on Ruby on Ales. It was originally designed as a single process that controlled everything using a GUI interface with a touch screen. Yeah, so have any of you also done any work in making graphical user interfaces with Ruby? There's a reason. I worked on that for a while. I actually wrapped, the Raspberry Pi comes with the binaries for OpenGL ES. I actually wrote a wrapper on top of that in order to use OpenGL to create 2D textures to create that interface. It worked really well for about a month, and then I wanted to change the interface, and then I threw it away. So now instead it runs a rack app that actually presents it, and I run everything in a browser to monitor, which causes the nice side effect that I can actually monitor what's going on in my brewery from anywhere. But I'm not that big of a control freak. I just log all the things. And then, so it's 2 separate processes. One is actually the monitoring of the state machine, and the other is the low-level interfacing with the GPIO. It allows me to separate those 2 things out so that if, for example, I turn off the control panel at home during the middle of a brew, it goes dark, but I don't automatically destroy everything because I have redundance on the mechanical side. So, something that's a little bit closer and more practical for the everyday person and not the people that want to go crazy and make a lot of beer is this thing called KeepMeAlive. I made this because, well, plants die a lot at my house. And I kind of got tired of them dying. So I designed this thing. It's just a basic moisture sensor. You can buy moisture sensors online for about $5, but I'm a cheapie. So you can actually use 2 galvanized nails hooked up to wire with a couple of resistors in order to run the wire through. It's not as accurate, but for all my purposes, I wanted to know if it was dying, not if it was decreasing its moisture sensor by 5%. So it works. So it reads it, and then it actually sends a text message if it hits a certain threshold saying, I'm about to die, please water me. And then you add all of these sensors in, and now things don't die. So I also have a version called Now it's not as bad as you'd expect. I don't have dead cats everywhere. But my particular cat will whine incessantly if it sees the bottom of the bowl. And it likes to whine in my room while I'm working, because I work from home. And I can't make the cat go away, and if I close the door, then the cat just tells me, hey, your door's closed. That's not allowed. So instead, I modified a cereal dispenser using a servo motor in order to rotate rotate just enough in order to dose it out. Then a Rails app handles scheduling when that servo motor should be triggered. And this gets me to one of the things that I find fascinating about embedded computing. As soon as you start getting into it and you start dealing with hobby electronics, is that there's so many, once you start getting into it, you get so many ideas on how to make things better. For example, KeepMeAlive.Animal. What could we do? Well, we could add in a webcam and be able to monitor the cat to make sure that it's eating. Or we could decide that we want to be able to trigger remotely, or we want to make sure that the cat isn't actually knocking over the food and then crying because it can see the bottom of the bowl. Any sorts of crazy extensions, these boards are giving us the opportunity to interface with it, and most importantly, doing it in Ruby. But all these routes have been using C Ruby in all of their implementations, and there are some drawbacks to it. C Ruby relies on a full operating system. These two particular boards work just fine for that, but if we wanted to expand into larger components or more complicated things, they don't necessarily have that capability. More importantly, memory usage is pretty large for Ruby, as well as its speed. Now, you see the asterisk compared to microcontroller real-time operating system stuff. Because you're running a threaded system that bounces from place to place, anything that requires a lot of accuracy and specific timings is going to be hard. So for example, if you wanted to make a quadcopter, it would be a little bit harder in order for you to be able to control. It's not impossible, but just expect that if one suddenly goes, wah, the operating system may not have enough time to jump back to your particular process, then register that there's an arm about to hit it, and then dodge out of the way. But hey, you threw your arm in front of it, it's your own fault. So in addition to that, one of the drawbacks that I didn't put on a bullet point here is that these processors are considerably smaller than what you're used to on a laptop. To compile MRI 1.9 when I started Ruby the first time, it was 2.5 hours to compile. I also screwed up and didn't expand the SD card, so it ran out of space in /TMP, and so it screwed up. I had to go through the entire process again. It's a very long time, so just expect that if you're going to use one of these things and use standard Ruby, start the compile process, go watch a movie, go outside, meditate for a while, try to meditate for at least 5 minutes, and then give up, something like that. So, if we've got this problem of Ruby not necessarily being able to fit in all of the places, because Ruby needs to go in all of the places, what are some approaches? Well, the first one that we're going to talk about is delegating to microcontroller units. We have the capability, we have these small microcontrollers. Why don't we have Ruby leverage as the state machine, focus on the overall scheme of things, and let the nitty-gritty GPIO interfacing and specific firing off the wires and the voltage level logic down to things that it was designed to do. So the idea here is you're using what's called the I2C communication protocol in order to have a bidirectional communication. It's essentially a trigger that says send and receive data whenever it's sending stuff down across the wire, wrap this. And then Ruby can wrap onto that using the wiring PI library. The example that I was going to post on here was like Zoom. You couldn't really see all of the code, so I just left it out. Instead, I will happily talk about how it writes and do some code example stuff with people after. But so that way you're programming your microcontroller with a very limited subset of tasks under one of those subsystems that I mentioned earlier, and then Ruby handles triggering when those things happen. What this also allows us is we get to have Arduino back again. We get the ability to use all those nifty things that are easy to get into. And in particular, it allows us to utilize the core of the Arduino, which is the ATmega328P. Don't worry, I'm not going to test you on that particular model number. It's just fun to really say ATmega328P. It's a really cheap microcontroller. It has a lot of input I/O capability, both digital and analog. Analog is the concept of not just binary on and off, but rather varying voltages means different things in terms of the logic. The other benefit here is that the Arduino Uno costs about $30, but that MCU only costs $2, and it's $3 worth of parts to run, so you can actually program using an Arduino Uno, and then pull the chip out, drop it into another thing, use $3 worth of parts, and buy another $2 chip, and you have infinite boards. But what I prefer is Mruby. Mruby is a subset of the Ruby API. I want more audience participation. Mruby. How many people know what it is? Oh yeah, that's a little depressing, but it's okay. Maybe 15 of you. Mruby, built by Mats, designed as a subset, running on an entirely new virtual machine. It's designed to be super fast, designed for embedded applications. It's supposed to go into your washing machine. if you really wanted to put Ruby in your washing machine. It's designed to cross-build to other targets so that you can do things like target the Arduino runtime. You can target different chipset systems. And it also doesn't have the concept of a standard threaded operating system. It doesn't know what a file system is. It doesn't know what multi-threading is. It doesn't know what because of that, it doesn't know what dynamic runtime evaluation of source code is within the particular Ruby VM. So mRuby's footprint is extremely small, about 80 kilobytes of SRAM, because it cut out a lot. C-Ruby, mRuby. C-Ruby, mRuby. There isn't a whole lot to it, which is good, and it's also bad, because a lot of the things that we've come to love, like Ruby gem support, you like all those gems that you wrote? Get rid of them. You can't use them anymore. You like the ability to use require? It's gone. Instead, you compile all of your source files in when you are building mRuby for a particular target, or you compile it down into bytecode and evaluate that within the context of the virtual machine. What this has resulted in is something called mgem. Mgem is the answer for mRuby's RubyGem equivalent, but it doesn't work the same way. A lot of people were very confused when the pull request first came out. The idea is that you're packaging up your C or Ruby code that you want to extend out there, and you include that at compile time, and the moment that you're running MIRB or running the binary for mRuby, that code is already there. There is no such thing as pulling in a require. Well, there's an mgem for it, but regardless, the idea is everything is self-contained, and most importantly, stdlib itself is just a series of mgems. The mRuby VM itself and the language, the entire thing is consisted of a few subset of the core underlying in order to get the code being evaluated and interpreted, and a series of mgems, which allows you to be able to not have that gigantic C-Ruby standard lib that has 1,000 things that most of you don't even know what are in there, and instead have only what matters, which cleans up the amount of memory utilized by a lot. Now because there's no such thing as Ruby gems, there is no master location automatically for being able to publish and pull these things. However, Daniel Bovensiepen, and I'm sure I just screwed up his name, is working on a list in a Git repo that contains everything that is currently known for mgem repos. It's a great opportunity if you want to just say, hey, does something already exist? It's a great place to start. And utilizing mgem is just a simple matter of adjusting your build config when you're compiling mRuby to add config.gem either from a GitHub URL where I'm adding in mRuby bid here, or if you want to do a local location, or if you aren't hosting all your code on GitHub, you silly people, but still use Git, then you can pass it a Git option. And as a result, down here you can see MIRB is being loaded up. I loaded in the PID library when I compiled, and now the PID global is already in place. There is no require, there is no craziness there. It's all part of the compiled end result. So why do we care from an embedded computing standpoint? Targets. We can cross-build mRuby to specific targets. In this instance, maybe we could, yeah, that's right, Arduino! I'm going to bring it right back to that. This little baby right here, this is I said earlier that Arduino can't handle Ruby. It's true, it can't handle Ruby, but it can handle mRuby, sort of. There is exactly one model of Arduino that can hold an mRuby VM running simultaneously, and that's the Arduino Do, which is because, like the Raspberry Pi and the BeagleBone Black, it's running on an ARM processor that has 512K? Yeah, a lot more than the 80 kilobytes that are necessary, sort of. No, this only has 96, so just enough. So what that allows us to do here is, I commented it out because building is complicated, but you're in build config, you're adding a cross-build option, so whenever you're compiling mRuby, you also are compiling your targets simultaneously because they rely on each other. And you get to pass in the configuration and compilation options that Arduino would normally have when it's building a program. It links in Arduino, and there's also a lovely library that I'm not even going to try his name, for mRuby Arduino, which actually creates the same programming interface that you would have writing an Arduino, only in Ruby code. You can get the full version there, because it's 300 lines of code. So, what are the steps then? If I can build mRuby on there, how do I actually get code out there? It's not nearly as much fun as with Ruby, where we save and we evaluate and that's it. Instead, you need to write your Ruby code. You need to then use mRuby's byte compiler in order to convert it into bytecode. I'm all over by 27 seconds. Oh, snap. We need to convert it to bytecode, then write C code that kicks off the bytecode in the Ruby VM, and then upload that resulting C code to Arduino. So what does that look like? It looks like that. So on the left, this is a rover example. Our rover has 2 wheels. It goes forward. Go forward interfaces with set motor. Set motor, in fact, tells us with forward direction because I cut out all the rest of the code in order to set the Arduino high and Arduino low values off of that. Then on the right side is the actual Arduino code that's being evaluated. We're pulling in mruby.h, the class value in irep. We are creating an entire instance of the Ruby VM there with mRB state at mirb. We're loading in the bytecode that is generated when we call mirbc on the left side. And then we are creating a new instance of the rover class and calling run on it, passing it no options. And we don't have anything in loop because Ruby handles all the fun time with the loop there. So that is an example of how we can write our Ruby code. We call bin mirbc. It creates bytecode. We save that bytecode, which is put in a file that refers to the rover bytecode and included. And it gets uploaded, and we have a rover. So let's see that rover in action. Because I happen to have a rover. And unlike Ruby on Rails, where I brought my Ruby control unit and the TSA broke it while my bags were being handled, this one actually still runs. I broke the clip, but unfortunately, it only runs on 2 wheels and is kind of low to the ground. But you get the idea. Happy rover running on mRuby. So I'm 3 minutes over. So my next one, I'm pretty sure says, always be coding robots. I'm not held responsible for the birth of Skynet as a result of following my instructions. This opens up a lot of opportunities that I think are great for Ruby to move into the physical computing scene. Unfortunately, mRuby is still alpha, so there's still a lot of work to be done, but I think that getting more awareness of its existence and people with enough passion to push it forward will make it just as important in my mind as web development. So, questions? Find the red mohawk. Thank you.